When you ask a physicist, "What exactly do you worship?" here is the answer you'll likely hear. A single theory that can describe every single behavior and movement of large stellar galaxies to small and strange quantum substances. A theory that brings together all the physical laws in our universe. I know what many of you are thinking. It's a very strange answer, but to a physicist, it's a profound one. Humanity's earliest question about our reality is, what are we made of? On the smallest scale possible, what are we made of? Some say we are made of atoms, but this is far from true. Atoms are composed of protons, neutrons, and electrons, but these particles themselves are not made of atoms. In fact, about 95% of the universe's energy and matter is attributed to mysterious entities known as dark matter and dark energy, and even these do not consist of atoms. Physicists like to reduce the description of the mechanics of our reality down to the simplest possible form. They expect this simplest form to have minimal parameters or moving parts. Our best theory in physics, called the Standard Model of Particle Physics, can describe most things with stunning accuracy, but it is still considered incomplete. This is because some parts of this theory require us to tune many mathematical parameters to get answers, and then there is gravity that does not fit into this at all. These problems caused physicists to search for a deeper theory that can bring all observable phenomena into a single mechanical framework. What will this theory look like, and how will it impact our understanding of reality and consciousness? To begin with, I want you to picture yourself in a room. You are alone, and you are trapped. There is a world out there, but you cannot visit it. The outside world is not completely inaccessible, though. You can view it through various windows in your room. I want to tell you briefly about two windows in your room that allow you to view the same reality, but twist it in dramatically different ways: the quantum window and the classical window. Using this analogy, you may think of quantum physics as the window into the true nature of reality, a glimpse into the hidden beauty of the universe. But in fact, this quantum window reveals a world that is not as predictable as we once believed. Instead, it's always changing, filled with possibilities and probabilities. It's a place where particles can be in two places at the same time, and where just observing something can alter the outcome of an experiment. The truth is that the quantum window does not actually reveal anything, but rather it distorts reality into a vision we can process and communicate with others in presumably similar rooms. You can think of the quantum window as a kind of stained glass kaleidoscope. It creates symmetry where there may be none and presents reality in a paradoxical way. But that doesn't mean it's all false. Some things become clearer when viewed through the quantum window compared to the classical window, so it's valuable to look through it. The classical window, on the other hand, offers a filtered view of reality, which can be somewhat misleading. It shows us a world that seems orderly, predictable, and controlled, but it falls short in capturing the true intricacies of the universe. This is the window that humanity has relied on for centuries, benefiting us greatly in various areas of science and technology. However, it can also lead us to overlook the genuine nature of reality. Neither window has an uncensored view of reality. Both have their strengths and limitations, offering different viewpoints on the same reality. The quantum window allows us to explore the extreme scales of the universe, while the classical window simplifies and makes our immediate surroundings more understandable. Together, they create a more comprehensive understanding of reality, yet neither can completely grasp the full complexity of the universe. In essence, maybe no window can do that. If you want to explain the universe and what goes on in it, we have a couple of tools at our disposal. If you want to explain atoms and subatomic particles, electromagnetism and nuclear forces, which are the basis of everything, the tool you will use is quantum field theory, which is a theoretical framework that combines classical field theory, special relativity, and quantum mechanics. And then, if you want to explain larger objects, you will need to use the general theory of relativity, the tool loved by classical physicists. If you aim to explain everything with a single theory, that would be the theory of everything, the coveted dream of every physicist. However, here's the challenge. We currently have two well-functioning theories that work seamlessly. Does this mean there are two separate theories of everything? Not at all, actually. You see, whether we realize it or not, there has to be only one comprehensive theory. And then some of you may ask, why can't we have two well-functioning theories? You see, black holes and the Big Bang pose a challenge for physicists because both quantum field theory and general relativity are effective in describing them. Typically, one theory explains the quantum universe, while the other clarifies the space-time fabric of the visible universe and massive objects within it. The issue arises because these two theories are largely independent, and using them together without significant changes to physics is problematic. So, why do both theories align with certain natural phenomena? And is the theory of everything inherently complex, or does it only seem complex when we combine the formulas we currently have? One proposed explanation for this complexity is what we call quantum gravity. So, with general relativity introduced in 1915 and quantum field theory completed in the 1970s, why haven't we been able to solve this mystery for so long? You could say maybe it's because we lack figures like Einstein, Heisenberg, Max Planck, Niels Bohr, or Oppenheimer today. However, we've inherited and expanded upon their achievements. We're not just standing on their shoulders, but collaborating with a multitude of brilliant minds, thousands of Einsteins, if you will. These individuals work together, utilizing the best available technologies. So if that's not the problem, what is it then? Gravity. Yeah, that's the problem. It is one of the fundamental forces and the most difficult to understand. It's hard to understand. It's very weak, and even though it's such a weak force, it's also a force that can dominate the entire cosmos. Gravity plays a crucial role in triggering some of the most energetically spectacular astrophysical events and giving rise to mysterious phenomena, such as black holes. So to understand the gravity that creates these mysterious phenomena, we must think at the level of quantum mechanics, that is, in the micro-universe. Take, for instance, the fact that the effects of quantum mechanics aren't observable in our bodies or in massive celestial bodies like Earth. This complexity makes understanding this force quite challenging. Consequently, we must search for quantum gravity in a setting where classical physics no longer applies, a place where a colossal mass is squeezed into a minuscule space, and this leads us to black holes. Now, you might wonder how we can use black holes as test subjects when it's impossible for us to go and experiment with them. You might ask, can't we create our own black hole? Even the close candidate CERN is insufficient for this task. We would need a collider capable of completing a full rotation around our solar system and more than a century of experiments in this tunnel to generate a black hole. Given the complexity of our task, and for those questioning where else we can find an answer, the key destination to explore is the Big Bang and the infant universe. Here, the cosmic microwave background, which we encounter constantly, has a very, very important task. After all, understanding light is understanding the universe, and this map we see is the first time light started to form after about 380,000 years after the Big Bang. If you've observed the image closely, you'll notice that the distribution of light appears irregular and chaotic. It's reminiscent of a double-slit experiment where photon packets seem to scatter randomly. However, these waves and uncertainties are incredibly significant. In fact, they exhibited properties of quantum mechanics when the universe itself was smaller than an atomic nucleus. It was vague and chaotic, not in the sense of disorder as we commonly understand it, but rather a chaotic order, a quantum-level order. Deciphering this map holds the key to solving numerous challenges, including the elusive theory of everything. This map represents the genesis of everything, portraying how a particle smaller than an atomic particle behaves due to its substantial and sudden expansion. So, where exactly should we direct our attention on this map? It conveys something, but what exactly? Nevertheless, the world of physics persistently formulates theories and diligently works on them while we contemplate their implications. For instance, there's the exploration of ripples in the fabric of space, particularly resulting from the merging of two black holes or the collision of neutron stars. However, a significant challenge in these experiments lies in detecting gravitons within these gravitational waves, a particle referred to as gravitational particles. To be specific, we're discussing a particle smaller than the Planck length, recognized as the smallest possible length in the universe. The Planck length is exceedingly minuscule. To provide a sense of scale, the Planck length is as many times smaller than an atom as an atom is smaller than the solar system. Extremely small. Let's not get ahead of ourselves. If, against the odds, the graviton is detected, a profound revolution in physics might be on the horizon. This discovery could prompt us to discard certain formulas and theories that, although considered correct, may prove to be inaccurate. In any case, the last tool in our arsenal is string theory, a theory specifically dedicated to quantum gravity. The concept of string theory originated in the 1960s when physicists were trying to comprehend hadrons. Hadrons are subatomic composite particles consisting of two or more quarks held together by the strong nuclear force, similar to how molecules are bound by the electromagnetic force. Protons, neutrons, and mesons fall into the category of hadrons, with mesons being a combination of a quark and an antiquark. While studying the peculiarities of interactions between pairs of mesons, particularly their relationship between angular momenta and masses, physicists suggested that the quarks inside the mesons are connected by strings. These strings can be envisioned as vibrating tubes made of gluons, which are elementary particles responsible for the exchange of the strong nuclear force between quarks. Physicists initially began working on a quantum theory to describe the strong nuclear force, but eventually shifted to quantum chromodynamics. This change occurred because the string theory of the strong nuclear force proposed vibrational modes of something unexpected and unwanted. In the realm of quantum fields, these vibrational modes are known as particles. These modes was what led physicists to discover the particle called graviton. Physicists realized that there was no apparent reason for the graviton to appear in the study of hadronic strings, leading to the abandonment of this theory. In the 1970s, physicists discovered that the mathematics of string theory could be applied to describe quantum gravity. After extensive and intricate mathematical work, along with some adjustments to the initial hadronic string theory, scientists achieved a breakthrough. On paper, this theory unified all the physical laws in our universe. However, to accomplish this, it introduced an additional 22 dimensions on top of our 3 spatial and 1 time dimensions, a version known as the bosonic string theory. Physicists then pondered why this theory couldn't explain not only force-carrying bosons, but also fermions, the particles like electrons and quarks that make up matter. They proposed the concept of supersymmetry to bring fermions and bosons into the same theoretical framework. Fermions are matter particles, and bosons are the force-carrying particles. By merging the principles of supersymmetry and string theory, they arrived at superstring theory. Supersymmetry suggests that for every boson, there is a fermion superpartner, and vice versa. This theory reduced the total dimensions from 26 to 10, deemed necessary to elucidate the true underlying nature of our reality. This marked the first superstring revolution, presenting 5 theories in which one-dimensional quantum strings moved around in 10 dimensions of spacetime. In physics, the concept of duality arises when different mathematical theories describe the same physical phenomena. Superstring theory is rich in dualities, presenting 5 distinct types of superstrings. In 1995, physicist Ed Witten unified these various forms into a singular framework called M-theory, requiring an additional dimension, bringing the total to 11 dimensions. Although there isn't a string theory in 11 dimensions, there exists a supersymmetric theory of gravity known as supergravity. Along with supergravity comes a theory of supermembranes. For M-theory to function in 11 dimensions, it includes surfaces called membranes. According to supergravity, the one-dimensional quantum strings can extend into different dimensions, forming a membrane-like structure. These membranes are dispersed throughout our universe, creating a hyperspace where the membranes exist with attached universes. These brane universes collectively make up the multiverse, with one of these branes representing our universe. M-theory strives to integrate the theory of general relativity, supersymmetry, and string theory. Physicist Ed Witten likened M-theory to a skeleton, with the 5 superstring theories representing individual bones. However, our comprehension of M-theory is far from comprehensive. Despite uncovering dualities in the strings and indications of supergravity, the core of the theory remains difficult to interpret. Even with our current understanding of this theory, we can predict and explain numerous phenomena that remained elusive with our best theories in physics. String theory provides insights into why gravity is weaker compared to the other three fundamental forces. It suggests that gravity extends through different brane universes, permeating our brane universe and reaching into others and higher dimensions. Another significant aspect it addresses is the origin of our universe. While our current best theories falter at explaining the moment of the Big Bang, string theory offers a distinct explanation of how universes come into existence. According to string theory, universes are born from collisions or separations of branes. This stands as the potential promise of string theory. Regrettably, there is currently no experimental evidence supporting string theory. The theory gained prominence primarily due to the mathematical framework surrounding it. Physicists have yet to discover concrete evidence or develop an experimental method to confirm the existence of the required extra dimensions. A significant challenge is posed by the incredibly small size of these quantum strings, estimated to be as tiny as 10 to the power of minus 33 centimeters in length. To observe these strings directly, we would need a particle collider that is 1,000,000 times more powerful than the Large Hadron Collider, and this collider may need to be the size of our entire galaxy. Such a colossal undertaking makes it currently impossible to directly observe the strings. Another significant challenge in proving string theory lies in the mathematical predictions it generates. Physicists theorize that the additional dimensions are compactified into a shape known as the Calabi-Yau shape. The behavior of quantum strings on these hyperdimensional surfaces is only comprehended in some idealized scenarios. However, the multitude of possible Calabi-Yau manifolds is staggering, with a minimum estimate of 10 to the power of 500 different topologies. Each compactified version of these dimensions implies distinct properties for vibrating strings, potentially leading to different sets of elementary particles and corresponding physical laws. The sheer variety makes it an immensely complex task to determine which set of properties corresponds to our universe. This complexity represents a significant hurdle in moving forward with string theory. However, our primary optimism with string theory lies in the potential proof of supersymmetry. Discovering the superpartners of elementary particles could potentially resolve numerous issues within the standard model. This exploration might also offer a means to detect the extra dimensions predicted by string theory. The conjecture that gravity is weaker compared to other forces stems from its purported operation in many more dimensions. According to this theory, the force-carrying particle of gravity, the graviton, should be capable of moving between these dimensions. If, for instance, a graviton were produced at the Large Hadron Collider and then moved to another dimension, it would appear as if energy had mysteriously vanished at the conclusion of the experiment. Currently, the most reliable experimental approach for string theory resides at a point beyond our current technological reach. Nevertheless, string theory consistently provides intriguing perspectives on seemingly insurmountable problems. While it's uncertain whether the story of string theory will culminate in being the theory of everything, it undeniably offers valuable insights. Despite potential inaccuracies or incompleteness in our current understanding of string theory, it could very well be the necessary step guiding us in the right direction. As a result, if it is not possible for us to observe a black hole or Big Bang moment, we can further work on string theory, which divides the universe into dimensions and tries to understand quantum gravity in those dimensions. But it's also a fact that we force particles, including gravitons, to be in one place all the time. We say they have to be in one place. Maybe that's the problem here. Just like Werner Heisenberg said, it's a chaotic order of uncertainties. Everything we observe and interact with is a manifestation of information. From the smallest subatomic particle to the vast expanse of the universe, the fundamental nature of reality is encoded in the form of information. Taking this perspective to heart eases the understanding of otherwise complicated ideas in physics and gives us insights into the nature of reality and our place in the cosmos. From an informational perspective, the concept of an observer-independent reality is unsustainable. Our comprehension of the universe relies on the information we gather, implying that the idea of reality is intrinsically connected to our experiences as observers. The process of acquiring information alters the content of the system, indicating that our perception of reality is not just influenced by the information received, but also by our active engagement as observers. Consequently, the notion of an observer-independent reality is deemed impossible. Now you may be concerned that this is starting to sound solipsistic. However, it is crucial to recognize that while our understanding of the universe is inherently tied to the information we receive and interpret, this does not imply that reality exists solely in our minds. Instead, our collective experience and intersubjective understanding of the world help to establish a shared sense of reality that transcends individual perceptions. Intersubjectivity involves multiple observers creating a shared understanding of reality. In the realm of information, intersubjectivity allows us to collectively establish a common sense of reality by agreeing on the significance and meaning of information. As we gather and experience information, we compare and reconcile our individual interpretations with others, refining our collective understanding of reality. This ongoing process enables us to build a consistent and coherent model of the universe that we can all share and agree upon. The emphasis on information's role in shaping our understanding of the cosmos isn't solipsistic, but acknowledges the inseparable link between our perception of reality and the information we acquire. In essence, reality is our shared knowledge of the world, underscoring that without our collective participation, there is no reality to speak of. With all that said, the truth is that, as humans, we experience the world through our senses and interpret this information through our consciousness. However, it is still unclear whether our perception of reality is a true representation of what actually exists or simply a construct of our minds. And, for every elegant, beautiful, compelling physical theory that's out there, there's an equally elegant, beautiful, and compelling physical theory that is wrong. In these matters, as in all scientific matters, it's up to humanity to ask the right questions. But it's up to the universe to tell us the answers. Whatever they are, that's the universe we have. It's up to us to figure out what those answers mean. And that's it for this video. Thanks for watching, and subscribe for more videos.